All right, Shal. Today we're going to be going over a little bit of oxidation number. Probably should have erased this before we got started, but we're good. So there's going to be three ways to think about oxidation number, but we're going to do a quick little detour on formal charge. So we'll use oxygen here as an example. So formal charge, right, is going to be calculated as an element's valence electron number minus, and so this is where they come in with a few different formulas. A lot of them will say minus the bonding electrons and minus the non-bonding electrons and 1/2 of the bonding electrons. We're going to do a cool thing I like to call circle. I like to simplify things as much as possible over here. So circle is you just count everything that's in the circle one time. So if you're astute and you know the formula that people usually use for formal charge, you'll notice that we're doing the exact same thing as that formula tells us to. We're subtracting the number of non-bonding electrons, the lone pairs, and 1/2 of the bonding electrons. So in this oxygen's case, we're going to count 1, 2, 3, 4, 5, 6, 7. So valence minus circle. And I even like to make it a little cuter. And I just say column minus circle, because we know that the column that an element's in will correspond to how many valence electrons it has. So in this oxygen's case, we're going to take column is 6. Oxygen is in group 6 minus that 7 that we just counted. And we're going to get -1. So we see an oxygen with 3 lone pairs and 1 bond. We know that the charge is -1. The formal charge is -1. Let's try that on our next oxygen here. So now we have an oxygen with 2 bonds and 2 lone pairs. So when we do our circle count, we're going to do 1, 2, 3, 4, 5, 6, and we get 6 minus 6 equals 0. No formal charge on this dude. And we know oxygen loves to have those 2 bonds and 2 lone pairs. Sometimes the 2 bonds would be a double bond in the case of like a carbonyl or carbon dioxide, right? All right, and then let's try this dude over here now. I'm going to do our formula, 6 minus, and then 1, 2, 3, 4, 5. So we have 6 minus 5 equals +1. So this oxygen is going to have a plus formal charge. So the reason that this method works, or the reasoning behind the formula you're usually seeing with formal charge being valence minus 1/2 bonding minus non-bonding electrons. The reason we have these formulas is because formal charge assumes that all bonds are non-polar, completely non-polar. So if this was like a carbon or this was like a hydrogen, we know those are polar bonds because oxygen is more electronegative than both of those fellas. But formal charge tells us, assume that these bonds that oxygen is making are completely non-polar. So that's why we only count 1 electron, because we assume, for the bonds, because we assume that the electrons are being shared evenly, and each of them has 1 electron we could call close to it. So that's the formal charge way of thinking about things. Now we said that oxidation number is going to think about things a little differently. So oxidation number, on the other hand, is going to consider all bonds to be completely ionic. So we're on the complete opposite spectrum compared to formal charge. So for example, if we look at, let's see, if we look at an alcohol. So we'll take ethanol here as an example. Oxidation number is going to consider those bonds. Any bond that's even a little bit polar is going to be completely ionic. What does that mean? Well, that means that if we draw our lone pairs here, how many electrons are actually close to this oxygen? Well, we have the 2 lone pairs. We know those are tightly held compared to bonds which are shared. But we're also going to take this carbon to oxygen bond here. And because oxygen is more electronegative, we're going to say that oxygen has all the electrons in that bond. And we're going to do the same with hydrogen. Okay. So this is going to leave hydrogen over here with no electrons, and we'll come back to carbon. So you can think of the oxidation number formula as being exactly the same as the valence number formula. The formal charge formula, in that oxidation number is equal to valence electrons, or column number, like we like to say, minus the electrons that are close to it. So in the case of oxygen, we're going to do the whole circle method one more time. And we're going to say, okay, oxygen's valence number is 6, but then it's hogging all the electrons in these bonds to carbon and hydrogen, right? So we're going to say 6 minus 1, 2, 3, 4, 5, 6, 7, 8, and we get -2. So this is going to turn out to be the case a lot of the time, right? We know oxygen do be loving to make 2 bonds to things. Oxygen likes to make 2 bonds, and it's usually more electronegative than whoever it's bonding to. We'll throw in our favorite electronegativity mnemonic, Fonkelbrish, for reference here. So oxygen is going to be more electronegative than pretty much whoever it's bonded to, and it's going to make 2 bonds. So it's always going to, it's mostly always going to have these 8 electrons close to it. Now let's go back over here to hydrogen. So we know hydrogen's valence number is 1, and oxygen stole its electrons from the electrons from hydrogen. Hydrogen has no electrons close to it. So hydrogen's going to be left with a +1 oxidation number. Now, if this -2 and this +1 looks familiar, it should, because if you remember your oxidation rules, we like to say that oxygen is usually -2 and hydrogen is usually +1. So this should be looking very familiar, even if it's in a sort of a new sense, a new way of thinking about it. And then I said we come back to carbon. So we have 2 different carbons here, right? We have 1 carbon who's bonded to an oxygen and 2 hydrogens, if we draw those fellas in. And we have another carbon who's attached to 1 other carbon, as well as 3 hydrogens. So if we look at those guys in their individual contexts, we'll notice that this carbon had its oxygen stolen by this oxygen here. So it's not going to get any oxygen, any electrons there. And if we refer back to our Fonkelbrish mnemonic, you see carbon's actually a little bit more electronegative than hydrogen. So for these 2 hydrogens, carbon is going to steal those electrons. Now in a carbon-to-carbon bond, right, we're going to have no such thing happening. And so this carbon and this carbon, they're each going to be getting 1 free radical. And then for our other carbon, it's going to have 3 hydrogens. It's going to be stealing all the electrons from them. Let's go ahead and circle them. You can see all these hydrogens are going to be +1, +1, +1, +1, +1, similar to our hydrogen over here. And then if we do our trick, carbon is in valence column 4. So we're going to do 4 minus, and then 1, 2, 3, 4, 5. We get -1. And then our other carbon over here is going to be 4 minus, and we got 1, 2, 3, 4, 5, 6, 7. So we get a -3. And that should sort of make sense that the carbon that's bonded to an oxygen has a higher oxidation number, -1, than the carbon that is not bonded to oxygen. It's just bonded to a carbon and 3 hydrogens, -3. Because since this carbon has a bond to oxygen, it should be more oxidized. And that is in fact what we see. So that's ethanol as an example. Now let's see what would happen. And I'm going to go ahead and I'm going to note these oxidation states that we just calculated because we spent so much work on them. What would happen if we oxidized this alcohol to an aldehyde? So now we're going to have a 2-carbon aldehyde. So the carbon in the middle here is going to have an additional bond to that oxygen. It loses a bond to hydrogen. This oxygen is going to have an additional bond to carbon, and it loses its bond to hydrogen here. And we can go ahead and fill in our lone pairs. So if you notice, that is actually one of our definitions of oxidation, right? Is loss of hydrogens, we like to say. Let's go ahead and see if that checks out with our formula. All right, so we'll start with oxygen up top, and oxygen up top is going to have its two lone pairs, and then it's going to steal the electrons in both of these bonds with carbon. And so we get 1, 2, 3, 4, 5, 6, 7, 8. We get 6 minus 8 is minus 2. So our oxidation rule is holding fast. Oxygen's making two bonds. It's more electronegative than carbon, who it's making the bonds to. So it's going to be minus 2. Okay. And then if we look at our carbon in the middle here, it's going to be our other carbon down here, right here, and then our hydrogen here. Okay. And oxygen already stole the electrons from these two bonds, so carbon's not working with very much here. It is going to steal the electrons being more electronegative than hydrogen here. It's going to steal both of these dudes. And then we're going to split this nonpolar bond evenly so that each of these dudes has 1. And now we can apply our formula and say carbon's column is 4, its valence number is 4, and it has 3 electrons close to it this time. So 4 minus 3 gives us +1. And then our carbon on the bottom left, our methyl carbon, just like before, it's going to steal all those electrons from the hydrogens, boom, 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 boom. And it's going to stay the same, right? This is the same configuration that we were looking at before. So 4 minus 7 minus 3. And then our hydrogen, of course, +1. So what we can note here is that the carbon who is a methyl is still a methyl, and its oxidation number did not change. Oxygen was making 2 bonds to elements that it was more electronegative to, and it is still making 2 bonds to an element it's more electronegative to, and therefore we can give it a -2 again. Carbon in the middle, this is what actually changed, right? We went from -1 to +1. And we know that if you're increasing an oxidation number, you're losing electrons. You see, Leo the lion says Gur, loses electrons oxidized. We lost 2 electrons. Or oil rig, oxidation is loss of electrons. Carbon lost 2 electrons. Now, what does it mean to say carbon lost these 2 electrons? Well, carbon only had 1 bond with oxygen who it was sharing electrons with. So it only had 1 opportunity for oxygen to steal its electrons. And now it had 2 opportunities for oxygen to steal the electrons of the bonds. And so that's one way to think about it, losing electrons. Now, this is going to work with all compounds because this is just purely working off the definition of what is oxidation number. However, this method is a little bit time consuming. We don't want to be drawing all of these dot structures. So let's simplify things a little bit here with a different example. Actually, before we do that other example, let's go through our exceptions here. So we remember that the oxidation rules tell us oxygen is usually -2, hydrogen is usually +1 with exceptions. We know the exception for both of them is when they're in a diatomic gas, such as O2 or H2. So I bet we can figure out why that exception exists and why the exception, this is not clear, why the number in the exception is 0 and 0. So let's go ahead and divvy up the electrons in these bonds. They're both non-polar. So each of those bonds is going to split evenly. And now if we apply our technique here, 6 minus, that's our valence number, 1, 2, 3, 4, 5, 6 equals 0. And likewise, 6 minus 6 is 0. So we can see why that's an exception now. And then we break up that bond between the hydrogens evenly because it is non-polar. We can go ahead and say 1 minus 1 equals 0 and 1 minus 1 equals 0. So here's where those exceptions are coming from. And then we know that we also have another exception, which is peroxides, such as hydrogen peroxide. And we know that in a peroxide, oxygen has a -1 oxidation number. So I bet we can figure out why that is now as well. So we'll use hydrogen peroxide as our example. Now, I did say that there's going to be an easier way to do this, where we're not actually doing this whole dot structure thing. And so let's modify our formula a little bit. And we can say that oxidation number is the sum on an atom of the formal charges plus the partial charges, the sum of the formal and partial charges. And so it looks different, but it's going to work exactly the same. So let's try it here. Between oxygen and hydrogen, oxygen is more electronegative. So we're going to give oxygen a partial negative charge. Now between oxygen and oxygen, we know that's a nonpolar bond. There will be no partial charges. But then if we look over here, our oxygen to hydrogen, oxygen's going to get the partial negative. Let's go ahead and give our hydrogens the corresponding partial positive charges. And let's see how this is going to work in our simplified formula. Sum of the partial and formal charges is -1. There's only one. And likewise over here, sum of the partial charges, -1. And that does correspond to our exception here. And we can see that the hydrogens are going to remain +1. And then our last exception we have is for hydrides. So metal is going to be me hydrides. And I always loved how the two exceptions were both 0, 0 and -1, -1. So the exception here, hydrogen, is -1. So thinking about our electronegativity, we can easily see why in a metal hydride such as sodium hydride, hydrogen is actually more electronegative than metals. So hydrogen is going to take both of those electrons, and sodium is going to be left with no electrons. And we know sodium is +1 valence, 1 valence, and then 0 electrons near it. So we're going to give it a +1. This is true for both oxidation number and formal charge. And then for formal charge of hydrogen, what we can say is that using our formal charge formula and our circle method, hydrogen's in valence 1 minus, and it has 2 electrons. So we'll give it a -1. So hydrides, we have a H minus where hydrogen has the lone pair. And we know that these hydrides are going to make great reducing agents as well as strong bases. All right, let's apply this formula now to an organic molecule. So we'll do, let's start with cyanide. Cyanide is a great element to know for the MCAT, as well as for life. And so in cyanide, we know that the formula is Cn minus. Who has the minus charge? Well, we know via our formal charge definition, we can do our circle, carbons in column 4, minus our column minus our circle. So 1, 2, 3, 4, 5. 4 minus 5 will give carbon the -1. And then just to check nitrogen as well, nitrogen's in column 5. So we'll give it a 5, and then 1, 2, 3, 4, 5, same as carbon. And however, nitrogen is happy to have 5 electrons, quote unquote, close to it. So nitrogen is perfectly happy that way, and it's going to not have a formal charge. Right? So, so we've established where that formal charge of cyanide is. I'm going to go ahead and redraw this so we can do now our oxidation number definition. So we said oxidation number is the sum of the formal and partial charges. Oops, sorry. Nope, not sorry. That was the right thing. Carbon and nitrogen, we can see nitrogen is going to be more electronegative than carbon. So then nitrogen is going to get partial negative, partial negative, partial negative. Sorry, those guys are all looking very different. 1 for each of the bonds to carbon. And then a carbon is going to get partial positive, partial positive, partial positive. One for each of the bonds to nitrogen. And if we count now the number of partial and formal charges, we had 3 partial positives on carbon, and we had 1 formal charge negative, totaling +2. So the oxidation number of carbon in cyanide is +2. And now we can go ahead and do the same for nitrogen here. And we can see that nitrogen is just going to have these 3 partial negatives. So the oxidation number is going to be -3. Now, what if we took a strong reducing agent, lithium aluminum hydride? If we took a strong reducing agent, lithium aluminum hydride, what functional group is this going to become? And of course, we know that strong reducing agents are going to reduce the heck out of this triple bond here, going to leave us with methylamine. Methylamine. Let's actually draw this big. Much better. All right, so here's our methylamine, aka CH3NH2, the simplest amine. And then we'll start with our carbon to nitrogen bond. Likewise, nitrogen is going to stay more electronegative than carbon. It's going to get a partial negative. Carbon's going to get a partial positive. And then between those carbon to hydrogen bonds, we're going to use the fact that carbon is slightly more electronegative than hydrogen to say carbon gets a partial negative, partial negative, partial negative. And then hydrogens are going to be getting partial positive, partial positive, partial positive for +1 oxidation states. So no exceptions for hydrogen here, right? Our hydrogen is staying the same as we usually see it. And then if we count now our sum of our partial and formal charges, then we're going to get 3 minuses and 1 plus. Oops, I can't see that. Get 3 minuses and 1 plus for a total of -2. And then if we look at our nitrogen and we finish doing the bonds here, we get partial negative, partial negative. And then we could go ahead and circle this guy. And we can count up our partial negatives. We have minus, minus, minus. And oh, the oxidation number of nitrogen stayed constant. So can we explain this carbon was reduced here, right? One of our definitions of reduction is gain of bonds to hydrogen, right? And carbon, in fact, did gain 3 bonds to hydrogen. So that's one way we could say it was reduced, or could say carbon also lost bonds to nitrogen. It lost bonds to an element that is more electronegative. And that's going to be one of our other definitions of reduction. We're going to have all these beautiful definitions in a moment. But we just want to pay attention to right now is that carbon gained 4 electrons, went from +2 to -2 oxidation state. And why did this happen? Carbon swapped, traded bonds from somebody who was more electronegative, who was stealing the electrons from it, and now to bonds to somebody that is more electropositive. So it can steal, carbon can steal those electrons. So that is how carbon is gaining electrons here. Why did nitrogen's oxidation number not change? Well, nitrogen was making 3 bonds to carbon, who is more electronegative. And now nitrogen is making 3 bonds to carbon, hydrogen, hydrogen, 3 bonds to elements that it is more electronegative than. So it went from having 3 bonds of an element it was more electronegative to 3 bonds to an element that it was more electronegative. And so its oxidation number shouldn't have changed because it is still stealing the same number of electrons from the bonds. All right, so let's summarize now. So we have our lovely our cheat sheet here, and now we know where all these numbers are coming from. We have our oxidation number formula, and one more formula we want to specify is that the sum of the oxidation numbers in a molecule is going to equal the net charge. This is very helpful for when you have something like permanganate, where you don't necessarily want to be drawing what that permanganate structure looks like on the MCAT. So instead, we're going to use our little cheat sheet here and our formula right here to say that manganese's oxidation number, whatever it may be, plus 4 times oxygen's oxidation number, which should be -2 because we're not in any of our exceptions. So the sum of the oxidation number should equal the net charge, which is a -1. And now we can plug in our -2. We're not on any of our exceptions. We get manganese -8 equals -1. Manganese is +7. All right, so this formula is always going to work. The one sort of like, or some of the scenarios where this formula is going to have the competitive advantage is, let's say you had a big giant molecule where you don't want to be summarizing 7 carbons and 8 nitrogens and 12 oxygens and 1,000,000 hydrogens, oxidation numbers to find the net charge, and then solving backwards to find carbon. Or in cases like we saw earlier, like in ethanol or something like acetic acid, where carbon is going to actually have 2 different oxidation states. So for like acetic acid, we couldn't just apply this formula here to solve for carbon's oxidation state because they're actually different, right? Instead, we'd be finding the average of their 2 oxidation states. So 2 formulas to think about in different scenarios. And then let's just finish our definitions of oxidation and reduction. So oil rig, or Leo the Lion says Gur. My alma mater is the Lion, so I prefer that one, but this one's the more well-known. And say oxidation is loss of electrons. And we went into what that actually meant functionally. And reduction is gain of electrons. And we talked about what that actually means, like structurally. So that's going to be our sort of, so it's just going to be our best definition. We're dealing with things like electrochemistry, galvanic cells and such. We could also say is that oxidation is gain. So this is going to be sort of the, this is going to be the more structural definition. For instance, when you're looking at a molecule like ethanol goes to acetic acid, you don't want to be calculating oxidation numbers. So we could say oxidation is gain of bonds to more electronegative elements, such as oxygen. So in this case, like we can see carbon had 1 bond to oxygen, it now has 3 bonds to oxygen. So carbon was oxidized because it gained bonds to more electronegative elements. It's not limited to oxygen though. As we saw earlier, you could be gaining or losing bonds to a nitrogen or something else, or something like a hydrogen. And we could also say oxidation is loss of bonds to less electronegative elements, such as when you're losing bonds to hydrogen. Okay. And then reduction is going to be the inverse of these two definitions. Looks like I'm running out of room here, so we're not going to have all of our definitions on the same slide anymore, but you can always rewind the video and see that. Reduction is gain of bonds to less electronegative elements, such as hydrogen. And that would make sense because if you are gaining bonds to less electronegative elements, you can steal their electrons. And therefore, you, as the atom getting the bond to hydrogen, are gaining electrons because you can steal the electrons in the bond to hydrogen now. Or loss of bonds to more En electronegative elements, such as oxygen. Loss of bonds to more electronegative elements, such as oxygen. And that would also make sense because elements like oxygen, they're going to be stealing your electrons. So if you're losing bonds to them, your perspective, you're actually gaining electrons. And then our final definition of oxidation and reduction, which goes back to oil rig. And this is the way that I like to do it because I don't like to think about electrons. I don't think about gaining and losing of negatives as much as oxidation is an increase in oxidation number. Reduction is a reduction or a decrease in oxidation number. But this fits very well with our other definition where oxidation is loss of electrons. So if you're losing electrons, you're gaining oxidation number. Reduction is gain of electrons. If you're gaining electrons, you're reducing your oxidation number because electrons are negative. So that's about it. And I hope this was helpful to you. This is how I think about redox on the MCAT. It makes things a whole lot more intuitive. It explains to me why our rules exist for oxygen and hydrogen. And it helps a lot for examples in larger structures where we're not easily able to calculate oxidation numbers by just applying our shortcut cheat sheet. So I bid you adieu.